Hey, good morning, everyone. Just a few announcements whilst the last few people are coming in. It's Wednesday, so the first online question is due today. I know that there have been some issues with the access to that. I can only apologize on behalf of the people that run that. It was a problem on the publisher's end with how they set up the textbooks, so it was kind of out of our control. If you have already completed online question 1, do not worry, we have a record of your results. You do not have to complete it again in the new course setup, okay? If you have any outstanding questions, please direct them to Adam. He will be able to deal with it. He's very good. Please be kind to him. He's been inundated with lots of queries. So please be patient, but rest assured, if you've already done OQ1 on the old course, you don't have to redo it on the new course, okay? So that was the main announcement. Just a few questions I've had about the general nature of the course as well. First of all, the scope of the course is quite broad. So this did used to be a more regular Calculus 2 course, where we spend lots of time on things like integration and so on. We tried to reduce some of the mathematical detail down and focus more on applications of maths to a broad range of topics in the life sciences. At the end of the day, you know, we have computers, we have calculators, we have things that can do lots of calculations. There's a certain extent to which you should know the underlying mathematics, but we're more concerned about making sure you guys can apply some of these ideas rather than spending ages maybe learning the underlying mathematical details. Okay, so you need to learn a certain amount, but that's why the course is a little bit broader. We're covering a broader range of topics because we're maybe going into a little less mathematical detail about some of those topics. Okay. So those are the main things, I think. Does anyone have any questions about that or about the nature of the course since we started? No? Okay, so today we're going to be talking about dot product. Can I have a quick show of hands who watched the pre-lecture material? Great, thanks very much. So last time we talked about vectors, and vectors are great ways of both storing data when we have multiple dimensions, as well as representing a direction and magnitude of something. Okay, so they can both represent data as well as tell us maybe about changes in data. So we talked about those antigenic maps where the flu virus was evolving. That tells us maybe about how much it's changing, but also what direction it's changing and how that might vary between years. So it can tell us something about the relationship between things. The rules for vector addition and subtraction are just like what we do with normal scalars. You just add or subtract the different components. We can also multiply vectors by scalars, and that can stretch them or shrink them or flip them in another direction, but they stay in the same overall direction, right? So they might get flipped around, but they're still pointing along what would be a straight line going through them. We can also pick vectors up and move them around. So they have an initial point and a terminal point, but the components tell us how much we're, say, moving in the x direction, how much we're moving in the y direction if it's a 2D vector. So it doesn't matter necessarily where they start and where they end. We can pick them up and move them around. So what about today? So today we're going to be talking about something called the dot product. And as you'll have seen from the pre-lecture material, this is a way in which we can multiply vectors together. Okay, so normally if you've got two scalars, you just take those, you take the product of them and you get another number. But what do we do if we've got two vectors? Well, it turns out there are different ways in which we can do something akin to multiplication with vectors. One of these is the dot product, which is sometimes referred to as the scalar product or the inner product. And what we do is we take two vectors, we do something to them, and then out of that we get a scalar. So whenever you're doing the dot product, if you take your vectors, you do the dot product, and you get a vector, you've done something wrong. You should always end up with a scalar. So we'll talk a little bit about what that represents and how this can be applied to a few biological examples. Okay. So in the pre-lecture material, we talked a little bit about what it means for vectors to be parallel or orthogonal. So orthogonal, perpendicular, at right angles. These are all the same things. And if we take our dot product, well, what do we need to do? We need to take each of our components. So remember, we're dealing with the x's, the y's, and the z's all together. So we multiply the x components, we multiply the y components. If it's in more dimensions, we carry that on, and then we sum those things together. So what does it mean then if we've got what does this dot product tell us then, I guess? Well, if we've got two vectors, u, v here, we take their dot product. That tells us something about the angle between those vectors. And it's kind of telling us about how much those vectors align. Okay, so if we have two vectors that are orthogonal, that means cos theta, we go down to our cos theta here, our cos theta at pi by 2 radians or 90 degrees is going to be 0. So that means that our dot product is going to be 0. So the dot product is a really good way of telling us whether we've got two vectors that are orthogonal, whether they're perpendicular to each other. If cos theta is equal to 1, that tells us that they're pointing in exactly the same direction, so they're overlapping each other. So we can use, there is a bit of a derivation down here. Don't worry about this bit in red too much at the bottom. That's just proving where this comes from. You don't need to like memorize that or anything, but we can use the law of cosines to build a relationship between the dot product and the lengths of those vectors and the cosine of the angle between them. So again, as with many things here, there is a geometric argument as well as an algebraic argument. There's a little bit in here about projections. Again, projections are a way of thinking about how we can find the relationship between two vectors. We can, if we've got two vectors like this, we can project one of these vectors onto the other, and it's telling us essentially how much of this vector is pointing in that direction. That's the component, or the scalar projection of one vector onto another. And the vector projection is telling us what happens if we take that component and then also multiply it by the vector that we had before. Okay, so a little bit about uses of the dot product. So I mentioned vectors are a way in which we can store data in many, many dimensions. One of the ways that we store your data from your grades from a course is in a vector. And then each of the different components of the course have different weightings. So for example, your OQs and your IQs each have 10% of the course. Midterms are 15%, and the final is 50%. So if we want to quickly combine all of those data together, we can have a vector of the weights, and we can have a vector of your scores. We take the dot product, and out of that, we get a scalar, which is your final score. This is a really nice, simple way in which we can combine these things together. We can also use the dot product to think something about the similarity between vectors. And this can maybe tell us something about which species we might have if we go out into the field and observe something, and we've got some previous measurements. We talked about this example with the irises in terms of points in a space, and then we worked out the distance between each of these reference measurements and our field observation. And then our first example was, well, we're going to assume that the one that is closest to those to the reference measurements is, or rather the field observation. When we take the distance, we minimize that distance to one of these reference observations, and that will tell us which one it's most likely to be. But of course, if you've got something that's growing in proportion, those proportions will change over time. Maybe you don't care so much about the exact distance, you care more about how it's growing in proportion. And that's thinking maybe about these as vectors rather than as points in a space. So this diagram down here, these different red dots are indicating, say, where each of these irises would be in, if we just reduce it down to 2 dimensions here for simplicity. We could draw these as vectors. We think about the angles that those vectors will create as coming from the origin. And maybe rather than the distance being the key thing from our field observation to our reference measurements, maybe we care more about the angle that this is creating with the axes, because things will tend to grow in proportion over time. So it will move along that vector. So the thing that tends to be closest, so it has the most similar angle, might be the better or more likely candidate for our field observation. Okay, one more thing as well. There are self-study questions at the end of the lectures and some of the problems sheets as well. Another question I had was about, why don't we cover these things in class? Well, these are self-study problems. It's kind of in the name. We don't have to include these things here. These are things that hopefully you'll go and do in your own time. Also things that you can go and talk to the TAs about or talk to me about at office hours. Try to give you guys as much practice of different types of questions as we can. I also won't always be able to go through all of the problems that are on the problem sheet in the problem class, because I want to leave time for you guys to actually work through them yourselves, to ask questions at the end. Again, they're there for additional practice with solutions provided. Okay, so don't expect us to necessarily go through everything that is on the problem sheets in the problem class. Okay, any questions? Okay, let's go through some problems then. Okay, just to get you guys warmed up and thinking about the dot product, we're just going to quickly run through these different examples here. So we've got u, v, and w are vectors in some n-dimensional space, Rn. And I want to know which of these are defined. Okay, so how about the first one? We've got u dot v plus w. Is this defined or undefined? Hands up for defined. Hands up for undefined. Hands up for I don't know or don't care. Okay, it is undefined. Can anyone tell me the reason? Yeah.
Because u times v will be a scalar.
Exactly. So when we do u dot v, we get a scalar. I'm just going to put s for scalar. W is a vector. Remember when we're doing vector addition, we need to add the different components of the vector together. But a scalar only has one component. The vector has n components here. We can't do that addition here. So this is undefined. Okay, how about u dot v times by w? Hands up for defined. Hands up for undefined. Hands up for don't care. Okay. This is defined. Again, u dot v is a scalar. W is a vector. So we've got a scalar times a vector. That's all that's doing is stretching this vector w by a factor of u dot v. Third one, u dot v dotted with w. Defined or undefined? Defined, hands up. Undefined, hands up. Undefined. Controversial. Oh, sorry, that is dot product. Apologies. I'm reading. So let me do that one again. Okay, u dot v dotted with w. Undefined, hands up. Defined, hands up. Undefined. Right. Scalar dotted with a vector. Okay. So u dot v we do first of all, and we get out of that a scalar. And then we're trying to take the dot product between a scalar and a vector. We can't do a dot product between a scalar and a vector. We have to do a dot product between vector and vector. So this is undefined. Question?
With the confusion that we didn't add, how do you want to write multiplication on it?
That is a good question. If you're doing multiplication between scalars, a dot is fine because it is clearly defined. If you are using the context of vectors, a dot means the dot product. Because like I said, we don't have, I guess if you wanted to say do a scalar multiplied by a vector, you would write it as, just remove this, you'd write it like this, okay? So we've got a scalar u dot v in brackets. Out of that comes some scalar c, let's just call it. That would just be c times by w. You wouldn't put a dot between those things. So it's an important question in terms of notation. When we're talking about two scalars, often we will put a dot because it's clear that we're talking about scalar times scalar. If we have a vector there, the dot means something very specific. It means dot product. So you just need to be clear if you're talking about scalars or if you're talking about vectors. If you're talking about scalars, it's fine to use the dot. If you're talking about vectors, dot means specifically dot product. So I wouldn't do scalar dot vector to indicate multiplication of the vector by the scalar. Because now we're in the context of vectors, we're implying there's something about a dot product. So if you want to multiply a vector by a scalar, just write the scalar, then the vector. Okay, so rather than c dot v, if c is a scalar and v is a vector, just write cv. Okay, is that clear? Okay. Last one, u dot v times by the length of w. Is this defined? Undefined? It's defined. So we've got a scalar times a scalar. So scalar here and scalar here. Remember, the length of a vector is a scalar. It's just measuring how long that vector is. Okay, true or false? If u dot v is equal to 0, then either u is equal to 0, the vector u is the 0 vector, or the vector v is the 0 vector. Is this true? Hands up. Is this false? Hands up. It's false. Why is that? Let's think of an example. Stick to 2 dimensions for simplicity. Suppose we've got 1, 0 dotted with 0, 1. These vectors are perpendicular. One's pointing up towards the x-axis, one's pointing in the direction of the y-axis. They're perpendicular. If you recall, if our vectors are perpendicular, the cosine of the angle between them is going to be 90 degrees or pi by 2 radians. So cos theta, in that case, is going to be 0. So when we do the dot product, we end up with a 0. How about the projection of v onto u is equal to the projection of u onto v? Is this true? Is it false? It's false. So I'm not going to write out the equation here. It's on the solutions, but this is false. Just because you're projecting one vector onto another, it doesn't imply that the same projecting that vector onto the other one is going to be the same thing. This is because they have the different components. If u dot v is equal to 0, then u and v are orthogonal. Is this true? Is it false? It's false. Reason being, we could have the 0 vector. So if all of the components of our vector are equal to 0, then our dot product is going to equal to 0. They're not orthogonal in this case. This is a little bit of a trick question, but it's just to remind you that just because u dot v is equal to 0, first of all, doesn't mean that u is equal to 0 or v is equal to 0, but they could be equal to 0, okay? Okay, let's move on to some calculations. Okay, like I said before, I don't want to spend loads of time with you guys just going through mathematical calculations that are out of context of biological problems. But in this instance, just to get you guys thinking about how we work with these and make sure you're comfortable with that, have a go at working through some of these problems. I'll walk around, and if you have any questions about the dot product or any of the things that we've gone through so far, please do ask me, okay? Okay, guys, I'll run through this. There's a little bit of confusion about how we get, say, the length of the vectors and how this relates to dot product, okay? So u dot u, we've got these vectors in R3, u and v that are defined. U dot u, how do we calculate that? Well, let's just calculate it. First of all, so we've got 2, minus 1, 1, dotted with 1, 1, 2. So remember, we take the x components, multiply them together, add them to the product. Oh, sorry, I've done v here, haven't I? Because I'm an idiot. 2, minus 1, 1. Sorry. So we take the x components, multiply them together. We take the y components, multiply them together. Take the z components, multiply them together. Add those things together. Okay, so we've got 2 times by 2, so we've got 2 squared plus minus 1 squared plus 1 squared. So we've got 2 squared, which is 4, plus 1 squared, which is 1, plus minus 1 squared, which is also 1. So this is 6. Notice that this is very similar to our distance calculation. I'm just going to draw this in here, this square root. Because if I'd done this instead and taken the square root of that, I would have got the length or the magnitude of this vector u. Okay, so that tells me that this 6 here is actually the length of u squared. So if I'd taken the square root of that 2 squared plus minus 1 squared plus 1 squared, I would have got the length of u. Because I didn't take the square root, I've got the length of u squared. So if you want to work out the length of a vector, you just take the dot product of that vector with itself. Okay, u dot v. So we've got 2, minus 1, 1, dotted with 1, 1, 2. Just very quickly, does it matter if I do u dot v or v dot u? No? So it doesn't matter which way around we do these things, you get the same answer. So what's this? We've got 2 times by 1, which is 2, plus minus 1 times by 1, which is minus 1, plus 1 times by 2, which is 2. So 4 minus 1, so this is 3. Again, if we had done v dot v, which we've not done yet, then we would have ended up with the length squared. Because it's u dot v, this doesn't have the same meaning. This is not the length squared. This is something about how we're combining u and v as vectors. Okay, so part 3, the angle between u and v. So this one caused a little bit of confusion. So the formula that was introduced for u dot v with the cosine is u dot v is going to equal the length of u times by the length of v times by the cosine of the angle between them. So if we've got our u and v look something like this, this is the angle between them. So what do we know so far? Well, we've already worked out what the length of u squared is. So we already know this bit. We've worked out u dot v, so we already know this bit. The only thing we don't know is cos theta, and we're trying to find theta and the length of v. But we can work out the length of v just by doing v dot v. So what is v dot v? Well, v dot v is just going to be the square of each of the components of v. So we have 1 squared plus 1 squared plus 2 squared. We sum those components squared together. So that gives us 6. Remember, this is the length of v squared, and we want the length of v rather than the length of v squared, so we just need to square root that as well, okay? So now we know this final bit here. So we know this bit here. So we could just do a little bit of algebra, rearrange this, and we can get an equation in terms of cos theta. So cos theta is going to be u dot v over the length of u times by the length of v. U dot v from above is 3. Length of u is root 6. Length of v is root 6. So root 6 times root 6 is just going to be 6. So it's going to be a half. So cos theta is equal to a half. So therefore, if we take inverse cosine of a half, we are going to get pi by 3 radians, or 60 degrees. Unless the question specifies, I'm never going to care whether you put your answer in radians or degrees, unless it says what is the answer in degrees or what is the answer in radians. Okay, I really care about making sure that you know how to do the steps to get to the final answer, rather than necessarily the presentation of that final answer, unless it's specified in a question. Okay, so if you put it in radians or if you prefer degrees, that's fine by me. Okay, the last part is working out the projection of v onto u. I'm going to do this over here. I've not got too much space, but let's see. So we're going to work out the projection of v onto u. Remember, the formula for this is going to be u dot v over the length of u squared times by our vector u. So we already know all of these things, right? We know what u dot v is. U dot v was 3. The length of u squared, that's u dot u, and that was 6. And we have our vector u, which is 2 minus 1, 1. So we just got a half, which is a scalar, times by this vector. So we can just move it inside. We're going to have 1 minus a half, a half. So that's our projection of v onto u. Now, I appreciate this idea of a dot product and projections is new to you guys. So take a little bit of time outside the lecture to practice a few examples. You can come up with some examples of your own. You can also pretty just chuck these into Google or Wolfram Alpha. Who's heard of Wolfram Alpha before? Good, okay. So use some of these online tools, make up a vector, make up another vector, work out by hand what is the dot product or what is the projection, plug it into one of these online calculators. You can come up with your own examples, as many as you want, to try and test your knowledge, okay? To make sure you understand how to do dot product, how to do projections, okay? Okay, I'm going to leave the next one, these questions here. The solutions will be online as with everything, okay? So here we're just working out unit vectors. You should be comfortable manipulating unit vectors, okay? Remember, a unit vector has length 1. So we may end up with a vector and we might need to multiply that by a scalar to make it have length 1. So just remember that when we do this. Okay, let's think of a biological problem. So suppose we've got a population, in this case, a population of fish. We've got females who are 1 year old, and we have A females that are 1 year old, so A is just a number. We've got B females that are 2 to 4 years old, and C females that are 5 years or older. So these females of different ages produce different amounts of offspring. So we can think about the total number of offspring are produced by taking the dot product of the population size for each of these different age classes of females with how many offspring that they produce, okay? So we have, for example, a vector F, which is the vector of the population sizes of each of these different age groups. And this vector B, which you can think of as their fecundity. So it's the amount of offspring that each of those produces. So if we do F dot B, well, F dot B here is going to just be 15A plus 35B plus 20C. And that's just going to be total number of offspring produced. So this is an example of just a little bit like the example of grade weighting that I gave at the beginning, where if we've got two vectors describing information, so we've got population sizes, we've got fecundity. You could also do with other things. It could be, say, death rates for these different classes, and you can work out what are the total deaths. It could be the infection rates for those classes. It could be contact rates. Anything where you're trying to find out what is the total something from a population where there are different weights and different classes within those populations, we can combine these two things together using the dot product to get the total. Okay, so this is one really nice, simple application of dot product. Okay, this example here is just a calculation one. So I'll leave that again as an exercise. You're just substituting numbers in here and working out what is the total number of offspring produced. Okay, let's think about one more example. I'm going to go down to this anti-zero example at the bottom, actually. So I've talked repeatedly about this idea of antigenic evolution of viruses and how we can measure how viruses react with different antisera and then come up with some relationship between those viruses. Now, suppose the binding ability of these different strains here are known, and we can now, we've represented them previously as points, but now we're going to think of them as vectors. So let's call this, say, V1, this V2, and this V3. And we're going to say, suppose that there is a specialized vaccine for each of these different strains. And the binding ability of a new strain, so a new variant has emerged, and binding affinity is given by this vector here. Now, the question we have is which of these existing vaccines would be most likely to be effective with this strain? And we're going to assume that the vaccine that has the smallest angle, so the smallest angle is best. Okay, so rather than the distance between these things and treating them as points, we're going to say, okay, this new strain has emerged given by these measurements here. These are the reactions with the antisera, and we care not about the distance, but we care about the angle between these things. Okay, so how do we work this out? Well, we can use the dot product to work out the angle between this new strain, this new vector defined by this strain, and each of our reference ones. And the one with the smallest angle is going to be the one that is the best candidate vaccine. Okay, so have a go at working this out. Don't worry, if you don't have a calculator, just put it in calculator ready form. Okay, so just want you to spend a few moments thinking about how we would structure our answer. Don't worry too much if you don't have a calculator to work out the final answer. Okay, so think about the smallest angle is the one that will give us the best candidate vaccine against this new strain. Okay, it's just a few minutes left. So remember, we're interested in the angles here. A couple of people asked about how would we know in an exam? You know, I would always specify what our assumption is. So you can think about this compared to the previously we treated these as points, and now we're treating them as vectors. You might say, how do we know which one we're going to do? Well, in the previous examples, I was assuming, as my hypothesis, that the best vaccine is the one that is closest. So I'd be treating them as points there because I'm interested in the distance between our new strain and something was there before. Here, I'm assuming that the smallest angle is the best. So maybe we've got two scientists and they've got two competing hypotheses. This one thinks it's the points and the distance that matters. This one thinks that it's the angle that matters. And then you go out and you actually see what the real world measurements are for that vaccine. Okay. You go back then and you look at your two hypotheses and you see which one was the better hypothesis. So maybe then you find out that the angle one is actually the best one. And then in future, you know that it's the angle that matters. Okay, so often we don't know what the answer is. We have competing hypotheses, and the hypothesis that we start with affects maybe how we treat these things. So previously we treated them as points, now we treat them as vectors because our hypothesis has changed. Okay, so finding the angles. How do we do that? Well, we've got these different vectors here. If, say, we call the angle between A and V1 θ1, and then θ2 and θ3. Well, cos θ1 is just going to be V1 dot A over the length of V1 times by the length of A. Likewise, cos of θ2 is going to be V2 dot A over the length of V2 times by the length of A. And similarly for cos θ3. V3 dot A over the length of V3 times by the length of A. If you work these things out, they turn out to be pretty similar, but we're going to have θ1 should be roughly equal to 6.6 degrees. Just a minute, guys. You'll be free to go in just a second. Hold on. The second is 2.7 degrees, and the third is 6.1 degrees. So which is likely to be the best candidate vaccine? Strain 1, strain 2, or strain 3? Strain 2. Okay, thanks very much. I'll see you on Friday. I'll stick around if you have any questions.